Hello, everybody. So now we will start talking about the concentrations, and we will make this video as a quick review on the concentrations and the units of concentrations that we deal with. And this is important for a couple of reasons. The first is that the driving force in mass transfer is the concentration difference, and it's important to make sure that we understand the concentrations and we have a good idea of what they mean and what they represent, because this is the main driving force. If I don't understand what units we have, then it's going to be a problem. The second, which is an important reason actually, is that we will include in this revision the symbols that we use to describe each one of these units that we will deal with. And this is extremely important because there are units, or there are symbols here in that we will discuss, which are used in this textbook, which are sometimes different from the symbols that are used in other textbooks. And that's why it's important to make sure that we all agree on the same symbols for the units, so that when we see this symbol we understand what it represents, especially that this will be included in all the equations that we will see in the next chapters, in the diffusion, in the convection. So if you don't understand what the symbol represents, it's gonna be a problem later. So what we're gonna do is review the units that we use in the liquid phase and in the gas or vapor phase. So for the liquid phase, we will see we have mass fraction, mole fraction, mass concentration, and mole concentration. In the gas or vapor phase, we have the same four units, with the addition of partial pressure, which is one extra unit that's only used in case of vapor phase or gas phase. So for the liquid phase, the mass concentration, we give it the symbol rho A. So this is the mass concentration of component A, which is simply from the name, it's mass concentration. So it's a mass of the component A per unit volume of the mixture. Sometimes it's called the mass density. And we know that rho represents the density of a mixture, so it's the total mass of the mixture per unit volume. And this is the main difference between the mass concentration and the density. They're both divided by the unit volume of the mixture, but this is mass of a single component, while this is the mass of the whole mixture. So rho A is MA divided by the volume. This is the mathematical representation of it. And rho is MA divided by volume plus MB divided by volume, and so on. So the summation of all the mass concentrations is the density of the mixture. For the mass fraction, we give it the symbol omega A, which is this. And this is, as the name implies, it's the mass of a component divided by the total mass of the mixture, which equals to the density or the mass concentration of the component divided by the density of the mixture. And the summation, of course, of the mass fractions equals 1. Again, maybe the new piece of information here is that this is the symbol that we use for the mass fraction. For the molar concentration, it's the same like mass concentration, but instead of having mass, it is number of moles. And we can get a simple relation that relates the mass concentration to molar concentration, which is that the molar concentration equals mass concentration divided by the molecular weight. And as the mass fraction, we have mole fraction, which is the number of moles of the component divided by the total number of moles, which also equals to the concentration of the component A divided by the total concentration of the mixture, which is the total number of moles of the mixture, of all the components in the mixture, divided by the total volume. So this is the mole fraction. It's important to keep in mind, because we will come to this later, that the mole fraction, we represent it with the symbol XA. So this X represents the mole fraction in the liquid phase. For the gas phase, we have almost, as we said before, we have the same four units for concentration, but the extra unit that we use is the partial pressure. And the partial pressure is widely used as the main unit that we use to represent the concentration in the gas phase. And To understand what partial pressure means, let's say that we have a mixture like the one we see here. It's a mixture of two components, A and B, and these two components are enclosed in this place, and the pressure of the container is the result of the presence of the two components together. So if by some magical means we were able to remove component B out of the mixture and have only component A inside, then the pressure of the of this vessel with only this component inside in the same volume is called the partial pressure. So the definition of partial pressure is the pressure of the component if it's kept alone inside the same volume. And it's important to keep in mind that this is the same volume. So it's the pressure if it's occupying the whole volume by itself. And the equation that we use to predict or describe the behavior of the gas is called the equation of state. The most simple one of them is the ideal gas law, which can be applied at low pressures, 1 atmosphere, 2 atmospheres maximum. So this is the ideal gas law, which states that PV equals nRT, and P is the pressure. We know units of the pressure, atmosphere and bar and others. For the volume, V is the volume with the units of meter cube, millimeter, milliliter, or foot cube, whatever. N is the number of moles. R is the universal gas constant, which has many values depending on the unit that you're using. There is 8.314 if you're using joule per mole Kelvin. There is 0.082 if you're using liter atmosphere and mole Kelvin, and so on. And for the temperature, it's Celsius, Kelvin, Fahrenheit, Rankine, and so on. So this is the ideal gas law, and as you see, I apply here the total pressure, and N is the total number of moles. We can, since we are talking about the concentrations, we can apply this to partial pressures. So we can put the same equation in terms of partial pressure, and the only difference that will happen is that I will substitute here with the number of moles of the component. So this is partial pressure of component A, and this is the number of moles of component A. So, and again, I don't change the volume because the definition says that this is the pressure if the moles are occupying the same volume. So I'm not changing the volume. And from this, I can get a relation between the concentration and the partial pressure from this equation. If I divide N divided by V, and then it's going to be P equals to PA over RT. So this is the equation that represents or can be used to relate the concentration, the molar concentration, with the partial pressure in gas phase. And of course, the total concentration equals to the total pressure divided by RT. So this is a simple thing. For the mole fraction in the gas phase, this is the only thing that we will discuss in the gas phase that we discussed before in the liquid phase, which is the mole fraction. The mole fraction here, we give it the symbol Y, and this is important that we give it a symbol X in case of liquid phase or solid phase, but for the gas phase we give it a symbol Y. And the reason of this is that we deal a lot with the mole fractions between the gas and liquid phases simultaneously in many operations where we have mass transfer between gas and liquid phases, like distillation, like absorption, like stripping. And for all these, we write equations that include both mole fractions in the same equation. So you have to distinguish between them, and that's why we put both mole fractions in different symbols. And this is the reason. So for YA, this is the mole fraction in the gas phase, and equals to CA divided by C, and equals to partial pressure of A divided by P equals to NA divided by N total. And this relation that we see here is called the Dalton's law of partial pressure, and it states that the partial pressure is directly proportional to the mole fraction, which is very clear in this equation. In many cases, we need to get mole fractions by the knowledge of mass fraction, and the other way, or vice versa. And this is pretty simple, and like I usually do it by starting with the definitions, because this is the simplest way to do this. So if I have mole fraction and I want to convert it to mass fraction, so I'll start with the definition of mass fraction, which is the mass of component A divided by m total, which equals to n multiplied by molecular weight divided by sum of n multiplied by molecular weight. If I divide in numerator and denominator by n total, then this will be equals to the mole fraction. This is the mole fraction. So this is how I can get a relation between mass fraction and mole fraction, or get mass fraction as a function of mole fraction. And for a binary mixture, I can get it, just the denominator will change to be XA plus XB MB, which is a very simple and straightforward thing. For the other way, if I have mass fraction, I want to do or get mole fraction, I start with the definition of mole fraction, which is n divided by n total, and I get the definition of the number of moles, which is mass divided by molecular weight, and I divide both up and down by m total, which will be this shape, and this m over m total equals to the omega a, which is the mass fraction. So I can get now the mole fraction as a function of mass fraction, and I can apply this for a binary mixture. It's gonna be as you see here. So it's, again, it's a simple piece of cake. One table. This table was, I got it from the textbook, and it's a very nice table, and it summarizes almost everything that we mentioned in this video today. So it puts all the symbols with all the definitions, the mass, the density, mass concentration, mass fractions, the summations, and the relation between mass fractions and the mass concentrations. For molar concentration, we have the same thing for the liquid or solid phases, and for liquid or gas phases, I'm sorry. And as you see, the only difference here is that this is X and this is Y, as we said before. One last thing that I will mention in this video: if we have a mixture of gases and I want to calculate the use the equation for mass fractions instead of mole fractions. So we said before that this is PV equals nRT. So if I want to get, instead of, and we said that we can get a relation between the concentration and partial pressure, which is P over RT. But if I want to get a relation between the mass concentration, not the molar concentration, then I can kind of make a tweak to the equation. So I'm gonna substitute for N with M mass over molecular weight. And if I replace V with M, then it's gonna be PM equals rho ART. So it's partial pressure and the mass concentration. So it's a simple relation that I can use to apply for the gas phase to get a relation between partial pressure and mass concentration. If I apply with the total pressure, then I will put here the density of the mixture, which makes sense. But in this case, I have to use the molecular weight that represents the whole mixture, and that's why I call it the average molecular weight. And since it represents the mixture, then it should take into account the concentrations of each one of them and the mole fraction, or the molecular weight of each one of them. So let's say if I have a very heavy component in a very small concentration and a small component with a high concentration, then it's expected that the average molecular weight would be closer to the component that has higher concentration, which is the smaller component. So this is what the average molecular weight does. It is equal to the average, the mole fraction, the summation of mole fractions multiplied by the molecular weight. So this is how we do it for or with the knowledge of the mole fraction. But if with the knowledge of mass fraction, it's going to be 1 over average molecular weight equals to summation of mass fraction divided by the molecular weight of each component. So this is the last thing I'll mention today. And in the coming video, I will solve some examples just to make things easier and get used to the equations and the solution of these equations. So I'll see you then, inshallah. Goodbye.